Hi friends, this is the seventh lecture in the lecture series for the preparation of GATE in mechanical engineering, and this is a special lecture. In this we are providing you a capsule of conduction. So we are dealing with a capsule of conduction in this lecture. So conduction is nothing but a heat transport phenomena in a medium where there is a temperature gradient is existing. So if T1 greater than T1 greater than T2, some heat will flow like this. Okay, and this heat transfer rate is denoted by the letter Q dot, and this heat transfer rate Q dot by area will be given as minus K dt by dx, and this is nothing but the heat flux Q bar. It is nothing but the heat flux, and this equation is called the Fourier's empirical equation or Fourier's law of heat conduction. So this is the Fourier's law of heat conduction in one dimension. So in general, we can write this Fourier's law as Q bar will be is equal to minus K delta T, and this equation is called the general form of Fourier's law. Fourier's law. Okay. So in the chapter of conduction, we studied about the general form of heat conduction. General form of heat conduction, which is nothing but an energy balance in a body, particularly in an element, through which heat transfer is occurring by conduction. So by energy balance, we have written, we can write net rate of heat flux plus net rate of heat generation will be equal to net rate of change of internal energy. Okay, and this can be mathematically written as del dot K delta T plus Q dot G will be equal to rho C dot T by dot T, and this equation is the most general form of heat conduction. General form of heat conduction. Okay, so next, for isotropic material, this K will be constant, okay, in every direction. So we can write this general form of heat conduction equation as del square T plus Q dot G by K will be equal to 1 by alpha dot T by dot T, where alpha is the thermal diffusivity. Alpha is the thermal diffusivity, which is equal to K by rho C. So this particular equation, which is only used for the isotropic material, is called the Fourier-Biot equation, and this Fourier-Biot equation is having some special cases, that is for steady state heat conduction, that is dot T by dot T equal to 0, and with heat generation Q dot G not equal to 0, we can write this Fourier-Biot equation as del square T plus Q dot G by K will be equal to 0, and this equation is called the Poisson's equation. Okay, so this is the first special case. Second special case is for unsteady state heat conduction, that is dot T by dot T not equal to 0, but with no internal heat generation. So this can be written as mathematically del square T will be equal to 1 by alpha dot T by dot T, and this equation is called the famous diffusion equation. So this Fourier-Biot equation's third special case is for steady state heat conduction, that is dot T by dot T is equal to 0, and there is no internal heat generation, which is Q dot G is equal to 0. We can write this Fourier-Biot equation as del square T is equal to 0, and this particular equation is the famous Laplace equation. So these are the three special cases of the Fourier biotech equation, that is Laplace equation, diffusion equation, and Poisson equation. So next in the conduction we have studied about one-dimensional steady state heat conduction with no heat generation. In this particular case we studied about many geometries through which one-dimensional heat conduction is occurring, and for this case the governing equation was Laplace equation, that is del square T is equal to 0, which is the governing equation. Laplace equation, that is the governing equation. So let's tabulate all the cases, that is first of all the geometry, and then temperature distribution, that is T minus T1 by T2 minus T1, then the RTH, that is the thermal resistance. So we have dealt this steady one-dimensional heat conduction for three geometries, which are plane wall. For this plane wall we have found the temperature distribution as x by L, and this is linear in nature, and also the thermal conductivity thermal resistance as L by Ka, where K is the thermal conductivity, L is the length, and A is the area of the heat conduction. Next we dealt with hollow cylinder, and this hollow cylinder the temperature distribution was ln R minus ln R1 by ln R2 minus ln R1, and for this case the thermal resistance was ln R2 minus ln R1 by 2 pi KL. So next we dealt with the hollow sphere, and here in the hollow cylinder case the temperature profile was logarithmic. Please note the temperature profile was logarithmic. For the hollow sphere the temperature distribution was 1 by R minus 1 by R1 by 1 by R2 minus 1 by R1. Here we can see the temperature profile was hyperbolic in nature, and the thermal resistance was R2 minus R1 by 4 pi K R1 R2. Okay, so these are the geometries that we dealt in the steady state one-dimensional heat conduction, and just go through this table only and memorize this table, and from this table we can find the Q dot, that is the heat transfer rate for individual for plane wall or hollow cylinder or hollow sphere, as delta T by RTH, where RTH is the thermal resistance, and from this we can find the heat flux, that is Q dot by A, which is heat flux by direct substitutions. Okay, so that's it, that we studied about the one-dimensional heat conduction. And next in the heat conduction we dealt with the composite objects. So 1 minute, let me clarify this. We dealt with the composite objects. This composite objects is nothing but multiple plane walls or multiple hollow cylinders or multiple hollow spheres that are connected either in series or parallel configuration, and we study the steps that has to be followed to analyze all these cases. So the steps are: step 1, determine individual resistances, that is determine the resistance of each and every element. Then the step 2 was draw thermal circuit and determine the equivalent thermal resistance, and this equivalent thermal resistance for series configuration RTH equivalent was equal to R1 plus R2 plus etc plus Rn, and for this parallel configuration, this RTH equivalent was given by the equation 1 by RTH equivalent will be equal to 1 by R1 plus 1 by R2 plus etc plus 1 by Rn. So these are the equations that has to be followed. So in a similar way of heat transfer rate, we can write the heat transfer rate Q dot is equal to UA delta T over rho. Before that, we have to go through the last step, which is the third step that has to be followed in the analysis of this composite objects. In the third step, we have to determine the Q dot as delta T over all divided by RTH equivalent. Okay, so sometimes this heat transfer rate is written as Q dot is equal to UA delta T over all, and this U is called the overall heat transfer coefficient, and in a similar way like this, delta T overall by RTH equivalent, we can determine this UA is equal to 1 by RTH equivalent. So this overall heat transfer into area, heat transfer coefficient into area is nothing but the reciprocal of RTH equivalent. So that we studied in the conduction, and then the last case we dealt with critical radius of insulation. Critical radius of insulation, and this critical radius of insulation is nothing but a radius which is denoted as R star, and this is the radius at minimum RTH equivalent or at which maximum heat transfer rate, and this can be calculated as R star is equal to K insulation by HO for cylinder, and this can be calculated as R star is equal to K insulation 2 into K insulation by HO for sphere. So please note these two equations, and these equations are very important. And for this insulation, we can provide the insulation to reduce the heat transfer either in the inside or in the outside of the pipe. To reduce heat loss, two cases are there: within pipe or outside the pipe. To reduce the heat loss, we can provide this insulation either within the pipe or outside the pipe. So within pipe, the heat transfer rate versus radius will be, the plot will be like this, that is, this is the plot and this is the arrow, and this is the point R star, which is the critical radius of insulation. And if you reduce the radius, or if you are keeping our radius of the insulation less than that of the pipe, then what happens, this will be the heat transfer for this particular radius R, and this, if R less than RO, then heat transfer will reduces only. And if we are placing the insulation outside pipe, and that is R greater than RO, the graph will be like this, that is Q dot will be here, and this is R, and this is the curve, and this point is the maximum point, which is R star, and this is a particular point which is R plus. So to reduce the heat loss by providing the insulation outside the pipe, we have to keep the radius of insulation as greater than R plus. So then only heat transfer will reduces. Okay, so if we want to increase the heat loss, that is to increase heat loss, keep R is equal to R star. So that's it. These are the all things that we studied in the heat conduction. Okay, so this is the under cap